Hey, what's up? It's Dan from SageMathTutoring.com, and I have it would be a college level student who's taking a calculus class, pretty challenging calculus class actually, and she has a test coming up, and once again, I'm going to be working on the test review that she gave me so that she can look at it and use it as a study guide. So anyway, let's get right into it. So it says use the given graph of f to state the value of each quantity if it exists. So clearly we're dealing with limits. It's very common when you are first taking a calculus class. All right, so looking at the first problem, 1a, the limit as x approaches -6, and this little negative sign means from the left. Well, -6 would be 1, 2, 3, 4, 5, 6 right there. And as x approaches -6 from the left, that's corresponding with this, not this, so therefore the limit is, you can see visually, -1. Okay, let's look at B. X approaches -6 from the right, well that's referring to this one, and closed circle here, open circle here. It actually doesn't matter when it comes to limits, from the left or right. Limits have more to do with what the graph seems to be trying to do. Okay, so if there's an open circle, it's still the case that the graph seems to be trying to go up to the y value of 4. So 4 is right there. Let's see, the limit as x approaches -6 in general. Well, that does not exist. How did I know that? Now, I went over this with my students. I know that because when it comes to general limits, if you're going from the right and you're going from the left at the same time, you could try doing it with like 2 fingers at the same time. If they don't touch, then the general limit does not exist. This is the general limit because there's no plus sign or minus sign above this 6. It's a -6, but there's no plus or minus sign above the -6. Okay, looking at D, f of -6, that literally means what is the y value on the function when x is -6? Well, that would be this. The y value is not +4 because there's an open circle here, but when it comes to what is the actual function y value when x is -6, we're dealing with -1 right there. All right. Okie dokie, let's see, f of -3. -3 is right here, and it looks like there is a hole there. Looks like there's a hole there, unless I'm missing something here. Yeah, there's a hole there, so it does not exist. Alright, because once again, that is not a limit situation, that is a function situation. F of -3 is this kind of hole right there, so it doesn't exist. Okay, the limit as x approaches 3 from the right. So 3 is right here. Looks like there's an asymptote, goes all the way up there. So when you're tracing it from the right, that would be positive infinity because it shoots upward. As x approaches 3 from the left, it shoots downward, so that would be negative infinity. As x approaches 3 in general, well, that does not exist because your fingers do not touch if you go from the right and from the left as you approach 3. Alright, the limit, x approaches 8 from the left. Well, 8 is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so as x approaches 8 from the left, that would be negative infinity because it shoots downward. Same with this thing. Okay, and then we look at the limit as x approaches infinity. Let's see. Okay, well, the limit as x approaches infinity, well, that's like what y value does this graph seem to try to approach as we go infinitely to the right, right? Because x is approaching infinity, so we're moving infinitely to the right. What y value does the graph seem to be attempting to approach? And I would say that the y value that this graph seems to be moving towards is a 0. All right, because it's really the x-axis. There's the y value of 0, y value of 1, y value of 2. Here's the y value of 0. and it goes right across the x-axis, is essentially at a height of 0 on the y-axis. So there you go. As x approaches 5, 1, 2, 3, 4, 5, yeah, the limit clearly 0. Okay, because the right-hand limit leads to a y value of 0, and the left-handed limit also would move towards that y value of 0. They both meet. They're both moving in the same direction, so you're good to go there. For the record, as x approaches 8 from the left and as x approaches 8 from the right, they both go to negative infinity. So just for the record, the general limit does exist as x approaches 8 in general, and it would be negative infinity because this matches that. So if the left-hand limit matches the right-hand limit, then the general limit exists. All right, let's take a look at number 2. Use the graph of f from question 1 to answer the following question. State each x value at which f of x is discontinuous. All right, so I'm just going to stop there. I'm going to write number 2 over here. So discontinuous is when you play a game where you imagine you had to trace the graph with your finger, and you ask yourself, are there any moments where I have to lift my finger? And clearly, you know, moving along, boom, we have to lift our finger to get there. So clearly there is a discontinuity at negative 1, 2, 3, 4, 5, and 6. So one of the x values is negative 6. So state each x value. So I'm going to just write, we can say discontinuous at x equals negative 6. Where else? Let's see. Discontinuous right here, because we would have to lift our pencil to jump from this line to this line because there's a hole there. That is negative 3. So we could say negative 3. Where else? There is a hole right at negative 1. You'd have to lift your finger in that moment as well. There is a discontinuity at positive 3. There is a discontinuity at, I guess that was 8, right? Discontinuity at 8. And then they ask us, you know, what kind of discontinuity was it? And that is going to be, well, a hole, also known as a removable discontinuity. There's a jump discontinuity right here. And then there's like the asymptote, which sometimes, well, you could call that an infinite discontinuity. Occasionally you might get a different kind of discontinuity called an endpoint discontinuity as well. This graph seems to focus on jump discontinuity, removable, because there's a hole, asymptote, so therefore an infinite discontinuity. And that is all. So at negative 6 we have a jump. At negative 3 we have a removable. At negative 1, removable. At 3 we have a infinite. My handwriting's not that great, but you get the idea. And then at 8 we have infinite. Alright, so that is how to do 2a, looks like. State each x value at which f is not differentiable. Explain. Well, in order for a function to be, or graph to be differentiable, it has to be continuous. So basically all the places where this graph is not differentiable or not continuous, it's also not going to be differentiable. Once again, in order for it to be differentiable, it has to be continuous. So therefore, any moment on the graph where it's not continuous or discontinuous, that is also a place where it's not differentiable. Okay, so that would be the same answer. Okay, and the reason is because basically there's just a theorem that would say that if the graph is differentiable at a particular x value, then the graph is therefore continuous at that same x value. Okay, so that's something that you're going to have to just kind of memorize. I'm kind of talking to my student right now. I'm going to assume that she knows what I'm talking about. Let's see. Number 3. Given the following limits, calculate the limits below. If they exist, you must show how you arrived to your answer by using limit laws. So I went to the next slide and I just transferred the reference information here for A through D. So let's get going. Looking at A, well, actually, let's review this. The limit of g of x as x approaches 1 is -8, so let's just keep that in mind. And the limit of h of x as x approaches 1 is -4, so we're just going to keep that in mind. This one has to do with h of x, so the limit of 2 over h of x as x approaches 1 is going to be what? Well, in a way, you could think of this as a combination of some of the different laws where the 2 could go on the outside. For example, it could be rewritten as 2 limit approaches 1. This, and it's like 1 over h of x. I mean, you kind of think of it that way, but at the end of the day, I think it would be the division law. The h of x, this -4, that's going to go down there. All right, so that's going to be 2 over -4 at the end of the day, because this part is really going to be 1 over -4, okay, due to this information. And therefore, this is going to be -1/2. All right, so that is how you tackle that one right there. Looking at B, the limit of the cube root of g of x. The limit of the cube root of g of x as x approaches 1. Okay, so similarly, focusing on the functions right here, so that will definitely be a similar scenario where you could sort of substitute in this. So that's -8. Don't freak out if it's the cube root of -8. That's possible. It's not going to result in an imaginary number because it's the cube root, not a square root. And that ends up becoming -2. So that is that one. Okay, this one has both g of x and h of x in it, so actually just write that down real quick. The limit x approaches 1 of 5g of x minus 2 h of x. Okay. So first of all, that could be rewritten in such a way, it's kind of like distributing this limit thing. It's not really distribution, but you can think of this limit as applying to both of these terms right there. So let's rewrite it so that we can remind ourselves that that's definitely true. And going to have limit x approaches 1 here to h of x. Okay. So then you could take into account the fact that this coefficient could go on the outside also. So on the next line, we're going to stick the 5 on the outside with this g of x hanging out right here. Similarly, this 2 can go on the outside with this h of x right there. And this one's really straightforward at this point because we already know what the limit of g of x is. As x approaches 1, it's -8. And we already know what the limit of h of x is as x approaches 1. We know that that's -4. So that's going to be 5 times -8 minus, careful, I'm going to put brackets there, 2 times, was it -4? Looks like I didn't need the brackets, but I'm just in the habit of that when I'm subtracting an entire quantity. I'm just really careful with that. It's a habit. So we have negative 40 plus 8 equals negative 32, unless I'm making a careless mistake. That is correct. And finally, we have the limit as x approaches 1 g of x and h of x. In a similar way, you could think of this one as being such that the limit applies to the g of x and the h of x. I'm not going to write that right now because I'm sure my student gets the picture. But that would be literally just negative 8 times negative 4, which would be 32. All right. Sure, my student understands that. Let's keep going. Evaluate the given limits. Let's actually blow this up. Let's get rid of this. Let me get rid of these guys. Who needs it? All right, blowing this up. What do we got? Limit of sine of blah, 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 blah as x approaches 1. Okay, well, substituting the 1 into this, that would be pi over 2. What is sine pi over 2? Definitely helpful to get clear about the unit circle. So there it is. And sine of pi over 2, well, pi over 2 is right here. Sine corresponds with the y value, and the y value in that moment is 1. All right, looking at b. Substituting 4 would give me, looks like radical 5 over 0, and that's problematic because of the undefined scenario. It so happens that the limit here as x approaches 4 does not exist. Okay, and the reason is because there's nothing you can do to get rid of this denominator of x minus 4. You can't cancel it out. My student knows that often when there is a square root somewhere, you could do like a conjugate type deal. But just so you know, you can't multiply radical x plus 1 times a conjugate. I mean, you might be able to if there was like radical x plus 1 plus 2, and then you can multiply by the conjugate and kind of see if you could cancel out that negative 4. But unfortunately, there's actually nothing you can do in that case. I could already see this is probably going to be one of those conjugate scenarios, you know, and we'll see when we get there. But I hope that's clear to my students. There's nothing we can do with this to get rid or cancel out that x minus 4 down below. All right, and it so happens that this graph diverges as x approaches 4 from the right. We're going to be going up. As x approaches 4 from the left, we're going to be going down. All right, so just to be aware of that, let's see. This one, like I said, looks like a conjugate type scenario. So let's experiment and see what happens. If I was to multiply this with this one right here by the conjugate, what would it be? My plus 3. You got to do the same down below. Plus 5 plus 3 multiplied by the conjugate would give us h plus 5 minus 9 all over h minus 4 times that. Okay, so I'm kind of imagining that this equal sign didn't exist and we're just going through the motions here. Also, my student hopefully knows that you should write limit as x approaches 4 here. All right, for the sake of just moving through the video as quickly as possible, I'm not going to do that, but I want my student to remember to write that every single time. This is going to become h minus 4 right here. Okay, so let's just cut to the chase. That would cancel. With the bottom, we would be left with 1 up top, and that would be 1 over this, and then we could substitute the 4 in. That would be radical 9, which is 3, so 3 plus 3, obviously 6, so it looks like 1/6 is the answer to that one. All right, sorry for the mess. I'm going to try to make the next one a little bit cleaner. All right, so let's see. As x approaches 0, well, e to the 0, and keep in mind with the limit laws, the limit could get applied here and applied here, right? So the limit as x approaches 0 with that is going to be 1, because plugging in 0 as an exponent is going to give us 1. There's going to be cosine of 0, and cosine of 0 is 1. So that's going to be 1 times 1. That's 1. And so, pardon me, this is 1, and it's going to be times this is 1, and that's going to equal 1. All right, looking at this one, clearly we have an undefined scenario that is a problem. Let's see what we could do here. Often it's the case that you could multiply the top and the bottom by the LCM of these two denominators here. And the LCM of these two denominators would be the following. So I'm gonna turn this into a multiplication symbol. Please, my student, remember, really with every step you have to rewrite this. Don't forget that. Kind of setting somewhat of a bad example, but whatever. Efficiency is the name of the game at this point. So that's, 4 times x plus 4. That is the least common multiple of these guys. And when I multiply it times these, well, that's going to become the following. That's going to become 4 minus the entire quantity. When this gets multiplied here, the 4 cancels with that 4, and it ends up just becoming x plus 4. So it's going to be x plus 4 all over, keeping everything sort of separate in its own compartment. I'm going to write it actually as, it's x times 4 right here, so I'll call it 4x right there. So that's going to be 4x times x plus 4. Let's look at the next line. And that would be 4 minus, up top it's 4 minus x. And let's see, that would be 4 minus x minus another 4. So this 4 minus this 4 would cancel, and you would be left with just a negative x up top. So we have negative x all over 4x, x plus 4, and I'll do a little divider, and we are good to go because this x cancels with that x. This was the problematic x, and we're going to end up with negative 1 over 4 times this thing. Now let's just kind of work this out in our head right now. I'm plugging in 0. Well, that's negative 1 over 4 times 4. So that's going to be negative 1/16, unless I made a careless mistake. Negative 1/16. I don't think I did, though. Let's move on. Okay. Substituting 3, let's double check the bottom. That'd be 3 squared. That'd be 9 minus 15. That would be a negative 6 plus a 6, so that's a problem already. We got the undefined situation, but in this case, let's factor, top and the bottom. Let's factor it. Divider, factor the top and the bottom. Let's start with the top. It's going to be x. It's going to be x. We're going to have a 2. We're going to have a 3 for sure. Minus, plus. Down here, definitely x, 2 and 3 also, actually. But this time it's going to be minus, minus. And what would get canceled out? Looks like the x minus 3's would get canceled out. All right, so I'm going to just trust that my student recognizes that these would cancel, and therefore we could rewrite this as the limit. I'll be a good person and rewrite the limit thing. The limit as x approaches 3 of x plus 2 over x minus 2. Now we can work with the substitution. That's going to be 5 over 1, also known as 5. Alright, so that is that one. Looking at this guy. Infinity. Okay, if the exponents match, then you just pay attention to these. It's kind of like a weird property, but it's not weird. It's actually understandable when you dive into the y. But this is blowing up infinitely. This is blowing up infinitely. And it results in a situation where you just really want to pay attention to this ratio right here, 6 over 2. And that is 3. All right, moving through. The limit as x approaches infinity. Okay. Well, let's see. So, what I would like to do with this one, like a little divider here too, is rewrite it like this. It's a little easier on my brain when I put the negative exponents down below. And we have this. And makes it a little easier to sort of conceptualize what's going on here when you put it down here. So if you were to substitute infinity into that, if you think about it, like number one, E is just a constant, all right? So it's just a number. It might as well be 10, all right? Doesn't even matter. It's just like 2 point something. So when it's an exponent of infinity, that means that this denominator is blowing up. Now, if you have a numerator that stays the same, but a denominator that's blowing up, think about it. This number, when the denominator gets bigger and bigger and bigger and bigger, and the numerator stays the same, this number, the whole thing, becomes smaller. Infinitely so, right? Because think about it. Imagine you add 1/4. Well, that is certainly greater than 1/8, which is certainly greater than 1/25, which is certainly greater than 1/100th, right? So you can really see that if you keep the numerator the same, but you blow the denominator up, the number gets smaller and smaller and smaller, and you might as well just imagine that this thing poofs out of existence. Okay? That's a way of thinking about it. You can imagine that it poofs out of existence. And since that 9 over e to the x poofs out of existence, therefore, this is going to equal the thing that's left over, also known as 3. It's going to be, really it's going to be 0 plus 3, which is 3. Because this, again, vanish, we'll say, out of existence. Okay? All right. Approaching 2 from the right. So this one's sort of interesting. I mean, you could think of it as like breaking it apart, where it's like limit as x approaches 2 from the right of this guy separately, and then, like multiplying it times the limit x approaching 2 from the right of this. All right, so that's something that you could do to sort of split them apart. And the limit as x approaches 2 from the right, I mean, the to the right part doesn't matter as much. That's just going to be 2 minus 3. And that's going to be just a negative 1. And it's going to be multiplied times whatever this limit is right here. And if you're approaching 2 from the right, I mean, clearly the general limit of this doesn't exist, but again, it's 2 from the right, so you could always, like, investigate what happens here, where you get closer and closer to 2 from the right. So, like, 4 minus 2, like if you test it out, you could test out any value to the right of the x value of 2, since we're moving from the right, on the graph. So if you test it out at 4, that'd be 4 minus 2, which is 1/2. And then as you got closer to 2 from the right, you could test out a 3, and that will be 1 over 1, which is just 1. So we just went from 1/2 to 1. So as we got closer to 2 from the right, y is increasing. So we are looking at infinity there. All right, it's increasing. And another way of thinking about it is you could also imagine, like, since we're getting close to 2 from the right, you could try substituting in values for x that are like just above 2, just above 2. So for example, like 2.1, right? Well, that would be 1 over 2.1 minus 2. So that would be 1 over 0.1, which would make this a larger number. Anytime you have a number divided by like a decimal or a fraction, that actually blows the whole thing up a little bit. So that would be larger. 1 divided by 0.1, I think that's literally 10. And then if you tried a number that is even a little bit closer to 2 from the right, maybe like 2.01, well then it would be 1 over 0.01, which would be even larger, right? So the closer you get to the x value of 2 from the right, the bigger this whole thing gets, which also justifies calling it infinity. So we have -1 times infinity, so that's going to be negative infinity. Hopefully that makes sense to my student. Okay, so I am going to break this one apart too, so it's like easier to think about actually. So it's going to be limit 1 plus 1 over x. Now, this one is just going to be 1, okay? It's the limit of a constant there. So that just becomes 1. So it's going to be 1 plus whatever this is. And I'd be curious to test out a few values. And this time I think I'm going to use a table to maybe just make things a little less confusing. So test out a few values. And I'd like to test values where, as far as the x values I'm testing, they're getting closer and closer to 0 from the left. So I'm going to cut to the chase and get pretty close to 0 right away. I'll test these out. And let's see what happens. So, you know what, maybe we'll do another value. We could also test out what's less than, what's closer to 0 on the number line, moving from the left. I would say -1/4, right? So testing these out would give me the following. We've got 1 over -1. We've got 1 over -1/2. And we've got 1 over -1/4, which would give me the following. -1. This would be -2. And this would be -4. All right, so what do we have going on here? As we get closer to 0 on the number line, this becomes less and less and less and less, and that's going to be to infinity. So that's going to be negative infinity, and even though it's like 1 plus negative infinity, well, it's like the negative infinity essentially just wipes out this one. It's way too significant, just you know, overshines or outshines this 1, and that just becomes negative infinity right there. All right. Yes, so this one relies on you remembering that the sign, I'm going to use a over a. So the limit approaches, we'll call this a too, 0. Well, that equals, drum roll, 1. So, in other words, when you have some angle right here, and that number, you know, that corresponds with the angle, is the same as this number down here, then it could be 1. So in other words, if that was 7x, as long as that's 7x, and, you know, it's approaching 0, it's going to be a 1. All right. So I think my student is probably pretty good with that one, but of course the question is, what do we do? You know, what do we do then? In a case like this, well, you'd have to multiply this by 7 to force it to be 7, right? And I can't just multiply the bottom by 7. I also have to multiply the top by 7. Now, this 7 right here might be better thought of as being out front. All right, the numerator 7, you kind of stick that out front. You know, I'll just kind of rewrite it actually. So that would be 7 limit x approaches 0 sine 7x all over, guess what, 7x. And that becomes 7 times, what do you know, 1, also known as 7. Woo. That's that one. Boom. Okay, so this one right here relies on our ability to remember the following. Here's a nice limit to remember. We'll just use x's this time. Just remember, as x approaches 0, as long as this angle matches the denominator, so this could be 4x, as long as this is 4x, then it is true that this one equals not 1, but 0. All right? So as long as you remember that, you're good to go. So we could do something similar here, where we multiply the bottom by 4 to force it to be 4x so that it could match this. And we're going to multiply the top by 4. You probably want to put the 4 out here. But anyway, I'm going to save time by explaining to my students it's going to be 4 times this limit with 4x on the bottom. All right? In fact, just to make it easier, I'll put the 4 right here instead. And this whole thing ends up becoming 0, so it's going to be 4 times 0, and therefore the whole thing equals 0. So that's that one. Let's see, this one right here, as cosine approaches, let's see, so when a cosine of 0 is just 1, so if I'm not mistaken, that's just 0 plus 2 over 1, which is 2. I do not see any reason why that would not be the case, so that's that one. Let's see. Limit as x approaches pi over 2, so we could rewrite this one as follows. Limit x approaches pi over 2 sine squared x plus the limit cosine okay, well, sine of pi over 2, because it's really sine of pi over 2 squared, right? So sine of pi over 2 is 1. And we're going to add that to, oh, and 1 squared is just 1, by the way, right? And this is pi over 2. Not really sure why that happened. Cosine of pi over 2 is 0, so that's going to be 0 squared, so that's just 0. So that's going to be 1 at the end of the day. Alright, let's see. Given h of x is that, find the following. Make sure to define the function as a piecewise function. Right. Okay, so this is a case where it would be a good idea to immediately define it as a piecewise function. Very quickly about piecewise functions, just want to make sure my student understands this. Basically, let's say you had something like that. Well, clearly that equals 3. And if you have negative 3 in there, well, that equals 3 too. And what's important to recognize is that when the thing inside here is positive, it ends up just being the same thing. When the thing inside here is negative, it ends up being the opposite thing. Alright, so I want you to just, for those of you at home watching, or for my student who's watching, just to realize that in this case, if whatever is inside here is negative, then it ends up being the opposite. That's the right way to think about it. Alright? So how does that apply to our situation? Well, it applies because we could really use the same reasoning. I'm going to write it over here where it's like h of x equals the same thing when the thing inside is positive or 0. It's okay for this to be 0, right? So I'll write if x plus 8 is greater than 0. And but when x plus 8 is less than 0, well then it's the negative or the opposite. Alright. So once again, when the thing that's inside the absolute values is negative, it results in the opposite. Okay, that's the way to think about it. Now it so happens that this is sort of an ugly scenario. I see a few different things. First of all, we could certainly simplify these guys. We could reduce them. And these need to change too to be a little bit easier to think about. So imagine that really this is the piecewise function that we want. Let's just do this in our head. After factoring out a greatest common factor of 2, that's going to be 2 times x plus 8, and that's going to result in 1/2. Okay, so that's going to be 1/2 if x is greater than or equal to -8. Alright, that's how that works. This one right here, well, that's going to be -1/2 if x is less than -8. Interesting, huh? So when you set it up like that, it's a lot easier to solve these. Alright, so looking at letter I, the limit of this function as x approaches -8 from the right, well, everything to the right of -8 is right here. So that's going to be 1/2. As x approaches -8 from the left, that's all this stuff right here. It's going to be -1/2. And as x approaches -8 in general does not exist because they do not match. 1/2 and -1/2 do not match. Okay, as x approaches 1, well, that's clearly to the right of -8, so that's going to be 1/2. And as x approaches -11, well, the function's continuous there. That's certainly less than -8, so that corresponds with -1/2. So maybe it helps to see like the graph. The graph would look something like that, where this is corresponding with +1/2. This is at the level of -1/2, and this is -8, the x value. So when they're being wise guys and asking, as x approaches 1, where's the function at? Well, the x value of 1 is right here. Where's the function at? Clearly it's at +1/2. And when they're being wise guys and saying, when x approaches -11, where's the function? Well, that's clearly like over here, and it's continuous, so the function exists. You know, if you go from the right, it's going to be at -1/2, you know, the y value. If you go from the left, the y value is going to be -1/2, so the function, or the limit I should say, is -1/2 there. So we are good there. Hopefully my student understands that. Okay, so what else do we have with this one? Alright, as x approaches 3, we want to know the limit of this one. Okay, well, this is a general limit. They're not asking approaching 3 from the right or approaching 3 from the left. This is a general limit, which basically means that we, for my student at home, just know that when it's a general limit and they present you with the piecewise function, you can find the limit, and the limit exists. Well, first of all, the limit only exists if after substituting this matches that. And if the limit exists, the limit is whatever number these become. So let's find out. Plugging 3 in here, that's going to be 5/2. Take a mental note of that. In fact, I'm going to write it. 5/2. 5/2. What about this one? Plug in 3, that's going to be 12 minus 6, which is 6/3, which is 2. So, my friends, that limit does not exist. Why? Because that does not match that. All right, squeeze theorem. Let's see. All right, so squeeze theorem, first time there's mention of squeeze theorem on the review sheet. And I don't know how well versed my student is with the squeeze theorem because we haven't discussed it yet, but let's actually investigate this situation. I'm kind of tempted to investigate it because these are fairly easy to graph. So we'll start with this. It's 4 minus x squared. So that's going to be 2, 3, 4. That is something like this. Parabola. And this is 4 plus x squared. So that's 1, 2, 3, 4. And this one is like that. And I'll do a little green for under that. And I will do a little blue for under that. And apparently, we have some other function called f of x, which I will underline in yellow, that is between these, right? And who knows what f looks like? Maybe it's some weird squiggly ridiculous looking thing, okay? But it's between them. And when we say it's between them, we mean the height is between them, right? The height of this guy is between the y values are between. And if we want to use the squeeze theorem to find the limit as x approaches 0, well, number one, we can see it visually. Clearly, as x approaches 0, with this yellow guy, the limit is 4, right? I mean, we could really see that, even in this dumb, rough draft type graph. We could very clearly see that as x approaches 0 from the left, as x approaches 0 from the right, it's going to correspond with a y value of 4. Why? Because this yellow guy is wedged in between the green and blue graphs, right? And that's, in a sense, the essence of the squeeze theorem. And what the squeeze theorem really says is that the limit of this one as x approaches 0 is 4, and the limit of this guy as x approaches 0 is 4. And if the limit of this one as x approaches 0 matches the limit of this one as x approaches 0, then anything in between these guys has to be such that the limit is 4 when x approaches 0, or the limit is the same as these guys as x approaches 0. Now imagine you didn't draw it. Then you would have to just kind of be like, all right, well, what's the limit of 4 minus x squared as x approaches 0? And ask yourself, what's the limit 4 plus x squared, x approaches 0? And you would see clearly that that equals 0, or 4, pardon me. And this would be 4. So guess what? This one gotta be 4, because it's in between these two guys. All right, hopefully that makes sense. All right, next page. Give the precise mathematical definition for continuity at a point A by providing all 3 conditions. All right, the teacher is getting very formal on you, or demanding that you get formal with these definitions, but it's definitely good to know this stuff. So let's see. The first condition is that the limit as x approaches a, the limit of this function exists. Okay, that has to be true. The next criteria is that f of a exists. And I'll explain these in a moment. And the third condition is that this has to be true. Now, what the heck does this all mean? I mean, basically, it could be very confusing. So I'll try to verbally describe what's going on here for my students. So, you know the limit exists when the left-hand limit and the right-hand limit meet, right? So, you know, here's an example of a function where the left part meets the right part, right? Now, when you take the limit, like let's say this is a, might as well call that a. So when you analyze the limit as x approaches a from the left, it should meet the limit as x approaches a from the right, and you know it's continuous if this limit exists. In other words, these both have to be going, like veering towards the same y value. All right, so that's criteria 1. Now, criteria 1's not sufficient, because if you had a hole there, criteria 1 would be fulfilled, but then criteria 2 would not be fulfilled, because f of a has to exist also. So in other words, when x is a, there has to be a y value there. You know, there has to be, you know, a point there, right? It can't just be an empty hole. So it's really important, you know, to fill that in, you know, to make sure that f of a exists too. We can't just have an asymptote. We can't just have a gaping hole there. So we just really, by filling it in, we ensure that we're fulfilling criteria number 2. And then criteria 3 says that f of x has to equal f of a also. Now, that might seem obvious when you look at this graph. It's kind of like, okay, well, the limit, from the left and from the right, that has to equal f of a, also known as this y value right here. Well, it's not so obvious when you take into account what would happen if only these 2 criteria were fulfilled. In other words, you're not going to be able to understand the importance of this third one unless you imagined a situation where only these 2 criteria were fulfilled and that was not fulfilled. And the question is, what would that look like? Well, that would look like something like this. If you had a hole here, but then you had a point like that. So in this case, the limit as x approaches a certainly exists. It's as you go from the left, it goes here. As you go from the right, it goes here. So remember, limits have to do with what the graph seems to be trying to do. Well, it seems like the graph is trying to make its way to this y value from the left, and it seems like it's trying to make its way to that very same y value from the right. So we would say that the limit exists, right? And then criteria number 2 says f of a has to exist. In other words, there has to be a y value that corresponds with the x value of a. Well, here's the x value of a. And right here, f of a exists, right there. All right, on the actual function. The function is defined at this point. It so happens that the function is defined a little higher than where the limit is, but it's still defined, right? And that shows why criteria 3 is important. It has to be the case that the limit also equals where it's defined, okay? The limit also equals where it's defined. All right, I think that makes sense. And, to be thorough, we will plug that in. And now it is official. All 3 criteria are fulfilled. Determine if the function is continuous at the indicated value. If the function is not continuous, then determine the type of discontinuity. Make sure to support your answer by using the 3 conditions of continuity. Okay, so looking here, when x is 1, we plug in 1. Well, first of all, does the limit exist as x approaches 1? And it does. If you use substitution and you plug in 1, looks like you're going to get 7 minus 3, which is 4, plus 4, which is 8, plus 5, so that's going to be 13. 13, that's the limit. So the limit exists. Is the function defined at x equals 1? Well, yes, it's defined at x equals 1. When you substitute 1 in, you get 13, so it's most definitely defined at that x coordinate. And then does the actual function, as it's defined at x equals 1, does that equal the limit? Well, yes, it does. 13 matches the limit, which is 13. All right. Let's see, over here, we have a problem. Well, let's see if the limit exists. I know my student knows how to do that by doing substitution, but the problem is, if you plugged in 1/4 here, this would be 1 minus 1, which is 0. So that is a little bit problematic. I think I would like to investigate what's going on up here. It's a strong possibility that we could factor this. So we're going to keep the 4x minus 1 down below. See if we can factor the top. So 4x squared plus 3x. I like to do something called the bomb method, where I multiply these guys. I get -4. That's the magic number. I then ask myself what factors of -4 are such that I could add them and get a +3, and that would be a 4 and a -1 and a -1. So then I could rewrite this as the following, 4 minus 1. Then I could distribute the x here and here, and I would get 4x squared plus 4x minus x minus 1. And then I could factor by grouping, take a look at each of these at a time, and factor out the GCF. The GCF in this case would be that. So we have x plus 1. And if you do things correctly over here, it's going to be an x plus 1 over here. So this would be factoring out a negative 1. Give me that x plus 1. And then I keep that parentheses x plus 1, and I fill in the other parentheses with whatever is left over, namely 4x minus 1. So that's a way of factoring out that. And then we have this cancel. And at that point, we have x plus 1. So it's the case that the limit is going to be 1 1/4, because when you plug in 1/4 in here, it gives you that limit. But you know, I'm already seeing, maybe I shouldn't have even done this, because bottom line is f of x is not defined there. Not defined. And actually we knew that, you know, right out the gate when we plugged in 1/4 and we had that 0 there. So f of 1/4 is not defined, so this is not continuous. However, they did want to know if the function is not continuous, then determine the discontinuity. All right, in that case, it did make all of this worth it, because we know it's not defined, so it's not continuous. It's not defined here, so it's not continuous. But the question is, what kind of discontinuity was it? So here's the deal. If you can do this rigmarole and get this cancellation, and now you can proceed forward, and there's, you know, the limit is like 1 1/4 now. If you could perform that cancellation, then the discontinuity is a whole. All right? It's a whole. And it's a removable. You know, it's removable. Think of the word removable as fixable. The discontinuity is removable. In other words, the discontinuity is fixable. And you know it's fixable because you just fixed this situation by making it so that you can now find the limit using substitution. All right? You were able to cancel these, and therefore you fixed that situation, and therefore you're able to find the limit. So associate the word removable with fixable, because what are you removing? The discontinuity. You're removing the problem, so that means that it's a fixable situation. All right? It's the way that I ended up remembering it, something along those lines. All right, so looking here, I can already see that there's going to be something going on here, because when you try to find the limit, or you know, you're trying to find out if it's continuous at this value. Right here we have a problem, but let's see. If we were to bring that situation over here, the numerator would turn into x plus 5. You could factor it x minus 5, and that's over x minus 5. Clearly these cancel, giving me x plus 5. And when you plug in 5 for x, that's going to be 10. So let's see. This right here says that when x is 5, it's 0. I don't know, I kind of want to analyze this by looking at the top function. After we performed these cancellations, we were left with this x plus 5, and that's fairly easy to graph. That's going to be 1, 2, 3, 4, 5 with a slope of 1 over 1, so it's going to be something like this. But once it makes it to the value of 5 here, there's going to be a hole. Now, how do I know that it's a hole? I know it's a hole because there was this cancellation. If you could do this cancellation, that means there's a hole at the value of 5, at the value that would have caused it to be undefined in the first place. You could cancel out the troublesome denominator. Then there's a hole at whatever the value of x is that would have caused the problem. So there's a hole there. According to this, when x is 5, there is a point at 0. So the bottom piecewise function says it's this. So as far as the discontinuity, it looks like it's a removable because of the hole right there. All right, looking at this one, f of x equals blah, 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 blah. Okay, so that's a fraction right there, I guess. Okay, when x is 0, is it continuous? Well, anything to the 0 power is just 1, so that's going to be 1 over 1 plus 1, so that's going to be 1/2. And over here, when x is 0, it's going to just be 1 down here. So quickly graphing this scenario, we have this function here, which takes place at all the x values less than or equal to 0. Now, I don't even know what that looks like right out the gate, but let's just say it looks something like this. And then, boom, where does it land? It lands on the y value of 1/2 right there. Whereas this one is x squared plus 1. I actually do know what that looks like. That would look something like this. And there's a hole there. And that's the case when x is greater than 0. Okay, this is a jump discontinuity. All right, so it's not continuous. You know it's not continuous because these don't match when you plug in 0. All right, doesn't match. And it's a jump. All right, moving on. For what value of the constant c is the function f continuous on negative infinity to infinity? Let's see. Oh, plus c. Well, my thought is that if there's any discontinuity going on with this thing, it's going to take place when x is 0, right? So let's find a value of c that would force this function to arrive at the same y value and this function to arrive at the same y value when x is 0. So taking the top function, if I was to plug in 0 for x, we would end up with this. And that's really equal to e to the c power. And if I was to plug in 0 for x here, that would just be this. Now, again, here's my rationale once again for my students. If there's any discontinuity at all with these two, it's going to take place at this sort of breaking point, okay? So what we want to do is we want to force this function to arrive at the same y value, when x is 0, as the y value that this function would arrive at when x is 0. Now we already know what y value this function is going to arrive at when x is 0. It's going to arrive at the y value of 2. So even if you wanted to see like a graphical approach, this is for everything that x is less than 0. So this would be such that there would be a hole on 2, and then it kind of goes down like that. Now we want to ensure that this function, no matter what it looks like, you know, it was like, even if it looked like that, I mean, it is possible to kind of know what that looks like, but even if it looks something like that, we want to, in a sense, ensure that it lands on the y value of 2 when x is 0. So we're already plugged in x is, you know, the x value of 0. We substituted that in, and that leads us to e to the c power. So what we want to do is we want to, in a sense, force this e to the c power to equal 2. And the question is, okay, well, how could we do that? And I'll just have to erase this later. You could take the natural log of both sides. And this just becomes c. And that becomes the natural log of 2. All right. So that's the c value that would ensure that this function is continuous everywhere, namely at this potential breaking point. Hopefully that makes sense. All right. So once again, we have a scenario where there's a potential breaking point at this x value of 1. Now, for my student, I hope she knows you don't have to graph it, you know, every time. But for the sake of sort of ensuring that you understand what's going on, I'm going to kind of graph generally what's happening. So we have x squared minus 1 for x values greater than 1. So under normal circumstances, that's actually going to be like, under normal circumstances, it would be like this parabola that looks like that. All right. But the thing is we only want to take into account everything that's greater than or equal to 1. So that means we could erase this part away. Okay. And then we got to take into account the sine function. So this sine functions in general, I mean, they kind of look like that, you know. And in order for this whole piecewise function to be continuous, we need to ensure that the sine function lands right there. Okay. Now what we have to do is we got to get clear, what is this y value? Now visually it looks like 0, but that's only because I'm experienced and I knew to graph it that way. But let's say you didn't know that this y value is 0, and you want to force this function to meet at the y value of 0, or whatever y value that this function meets at when x is 1. So the first thing you need to do is figure out what is that y value. We could figure it out by plugging in 1 right here, and that would be 1 squared minus 1, which is 0. So that's the y value, the sacred y value, you know, or the height, also known as, you know, f of 1. All right. So that's the sacred y value that you're aiming this sine function at. So what you could do is you could force the sine function to equal 0 and figure out what c is. Now, we already know what x is. It's the x value in question, right? So that's going to be sine of 1 plus c equals 0. So the question is, what sine values or what angles are such that sine of that angle equals 0? And that would be pi and 2 pi or 0. So I'm going to say, I think it's safe to just pick one. So let's pick this one. And therefore, it's really the case that sine of 0 equals 0. And therefore we can set 1 plus c equal to this 0. This 1 plus c equal to this 0, because we know that sine of 0 equals 0, right? So sine of what equals 0? Well, sine of 0 equals 0. Therefore, we could say that 1 plus c equals 0, and then we could call c -1. I don't think that should be an issue. Again, we did choose one of the three possibilities. It's actually infinite possibilities, but these are the ones that are represented on, the typical unit circle. So I believe we're safe saying that c is -1. If c was -1, then this would be continuous. Okay, so determine if the function is continuous. Well, this is continuous because there's nothing that would cause a discontinuity here. All right, there's nothing that would cause a discontinuity, so therefore it's negative infinity to positive infinity. That's the interval by which it's continuous. All right, you could just sort of think of it as like the domain is all real numbers, because there's no x value that would result in a problem were we to substitute it in. Literally every x value could work here. There's no x value that would cause this to be undefined. There's no x value that would cause this to have an imaginary number, and so on. On the other hand, this one is such that there are potential x values that could cause this to be undefined, right? And if it's undefined, it's not continuous at that point. So we're going to have to be detectives and figure out what those x values are by forcing the denominator to equal 0, and then solve for x, and whatever that x value is, the culprit. I'm going to divide both sides by -3 because I don't like that negative leading coefficient. So that essentially changes the sign of everything. 0 divided by I'm dividing both sides by -1. I apologize. 0 divided by -1 is just 0. And then I could use the bomb method. If I multiply these two together, I get -6. That's the magic number. I ask myself what factors of -6 are such that when I add them, I get a +5. And that would be +6 and -1. So this could be rewritten as the following. That's 6 minus 1. And that could be rewritten as factoring by grouping gives me preserve the parentheses, make another parentheses. What goes in there? All the other stuff. Now we can clearly see that over here, -2 would cause that one to be 0. And then over here, you could do a little bit more legwork where you set 3x minus 1 equal to 0. And you would soon realize that x equals 1/3. So, in other words, when it comes to this one, the x value of 1/3 would cause this to be undefined, and the x value of -2 would cause it to be undefined. So on a number line, we have 1/3, which is a problem. We have -2, which is a problem. Now, I would advise kind of getting a sense of the number line for something like this, because if we're going to do the interval notation, it makes it a little bit easier. So we're looking at -infinity all the way up to -2, but not including -2, union with -2 to +1/3, union 1/3 to +infinity. All right, so that is the intervals within which this function is continuous. The discontinuities happen in between, all right? Namely when x is -2 and when x is 1/3. Okay, so you know that this is not continuous at the x values that would cause this to be a radical negative number. So what you could do is sort of be a detective in a similar fashion, only this time you're going to take this 5 minus 9x, and let's find out what x could be. I'm not going to care as much about what x can't be. I'm going to force this to be greater than or equal to 0, because all these x values could work, because as long as this is 0 or greater, this would remain a real number. If what's underneath here was negative, in other words less than 0, then we're in imaginary number land, and you know that the graph is discontinuous at that point. The graph doesn't even exist at that point, all right, when whatever x values would cause this whole thing to be negative, the graph doesn't even exist at that point. So we're, in a sense, figuring out what x values could be in this domain. And you could set it up by forcing what's underneath the radical to be positive or equal to 0. So I'm going to add 9x to both sides. I'm going to divide both sides by 9. So x has to be less than or equal to 5/9. I'm going to rewrite that because I think most people are used to seeing it with the x on the left. So x is less than or equal to 5/9 there. That's the domain. Now, what does that look like on a number line? Well, on a number line, oh, by the way, and that's the domain, that's also where this thing is continuous. All right, so here's 0. 5/9 is over here, and x could be 5/9, so that's a closed circle, and it goes in that direction. So what we're looking at is negative infinity all the way up to and including 5/9. Okay, so negative infinity all the way up to and including 5/9. So there can be a bracket there because 5/9 is included. Okay, looking at y equals cosine x. Well, that's continuous everywhere. There's no x value that would be troublesome in this case. Also, it helps to just know that the graph of cosine looks something like that, and it goes on forever. All right. So that's that. Use the intermediate value theorem to show that the function f of x has a 0 in the interval 1, 2. Okay, use the intermediate value theorem to show that the function f of x has a 0 in the interval 1 to 2. In other words, you know, if you got some graph, I mean, I don't know what this function looks like, but let's imagine, well, we are definitely analyzing the interval from 1 to 2. So let's say that's 1 and that's 2. It's not drawn to scale, but we want to see if there is a 0 somewhere in this interval. Now, what do they mean by a 0 in the interval? Well, what they mean is this function crosses through the x-axis somewhere in this interval. In this place where it crosses the x-axis, that's called a 0. All right. And one way to check is to plug in 1 and see if you get, you know, like a value like that. And if you plug in the x value of 2 into this and you get an x value or a y value that's like down below, then you know that if this thing is continuous, it had to have crossed through. So in other words, if you plug in an x value of 1 and you're up here, and then you plug in an x value of 2 and you're down here, then there's no way in hell you didn't cross through the x-axis to get there, right? And that's a way of proving that there's a 0 during that interval. Okay. Now, to be fair, maybe it's going to be a situation where it's like where it's like this, right? And that's fine, because we could clearly see if you plug in 1 into this and you get a value down here, and then you plug in 2 into this thing and you get a value up here, well, once again, you had to have crossed through the x-axis. So the bottom line is if you plug in 1 and then take note of the y value, and then you plug in 2 and then take note of the y value, if they have opposite signs, then the graph had to have gone through the x-axis. So let's investigate. Let's see what happens. So, checking out f of 1 first, why not? It's going to be cubed minus 6. I always like to draw into parentheses, as anyone who has seen the videos know. Plugging it in with 1, and what does that equal at the end of the day? That equals 4 minus 6, which is negative 2, minus 3, which is negative 5, minus 2, which is negative 7. All right, now all I need to know is if I plug in 2 into this and I get a positive number, which is the opposite sign of this number, then we're good. Now let's get a sense of this. 2 cubed, that's 8. So already we're at 42. 42 minus, looks like it would be 24. That lands me in, like, 20-something range. Plus 6 bumps me up a little bit. And then subtracting 2. This is definitely going to be positive. If I plug in a 2 into this thing, it starts at 40-something. Then we, in a sense, take away 20-something. But then we add 6, and then we subtract only 2. So that's clearly positive. Your teacher's probably going to want you to do that, but I'm running out of room. Okay, so my student who's watching, hopefully you just go ahead and just do that. All right. Let's see. Find the equation of the tangent line to the curve at the given point. Okay, well, in order to find an equation of a tangent line, in order to find an equation of any line, I mean, you need the point, but you're going to need the slope. Now, to get the slope, you could use the difference quotient. And difference quotient is such that it's a good idea to get clear about what f of x is, and then get clear about what f of x plus h is. Now, f of x is 3x squared minus x. And f of x plus h is going to be the same thing, only it's going to be this. Now I say, before we do anything, let's actually simplify this, all right, to avoid confusion. So we're going to have 3 times x squared plus 2hx plus h squared minus x minus h, also known as 3x squared plus 6hx plus 3h squared minus x minus h. And that is as simplified as it could be, even though it's very ugly. And the difference quotient is this. And this we just figured out in blue. And this we have right here. So this will be 3x squared plus 6hx plus 3h squared minus x minus h minus the entire 3x squared minus x all over h. And let's simplify that also. So we got 3x squared. That's going to cancel with this negative 3x squared. I don't mind just doing that right now. Let's also make sure we turn that into a plus in the meantime. So this cancels because, and that turns into a plus because the negative would go in there. So this positive x would cancel with this negative x. So let's get rid of that. And what else do we have? What we're going to have left is 6hx plus 3h squared minus h all over h, and then we could factor out an h for sure, and that becomes h times 6x plus 3h minus 1, and that's all over h, and then these would cancel, leaving me with 6x plus 3h minus 1. Now, in reality, it's a limit scenario. So, and you really should write that every single step, so I'm kind of bad, my bad. But it's a limit as h approaches 0. Let's get rid of that. And therefore, we could plug in 0 for h, which would result in just a 6x minus 1, because that would become 0. So that's really the derivative of 3x squared minus x. Now, the point that's of interest is 1, 2. And if we want to find the slope at that point, well, you could plug in that x coordinate right there. And you're going to get 6 times 1 minus 1, which is 5. And that's actually the slope. Once you have the slope and the point, you've got, the slope right here, we've got the point right there. Well, then you could just figure out the equation. And the slope, also known as 5, the point that is of interest is 1, 2. And really a classic way of going about it is to realize, y equals mx plus b. Well, we know that this one's going to be y equals 5x plus b. All right. Now the question is, what's b? Well, you could plug in the x and y coordinates here, so it's going to be 2, 5 times 1 plus b, and that's going to be b equals -3, and then finally you could rewrite the entire equation as y equals 5x minus 3. So that is that one. All right, what about this one, 8 over x plus 4? So we already have the point at 0, 2, using the difference quotient. Let's see what we can do with this one. And f of x in this case is 8 over x plus 4. F of x plus h is 8 over x plus h plus 4. So we are looking at 8 over x plus h plus 4 minus 8 over x plus 4 all over h, and still a limit. Problem? And let's see. For this one, we're going to have to multiply the top and the bottom by the LCM of these. And the LCM is the following. It is, I'm actually going to give it 2 parentheses. It's x plus 4 and x plus h plus 4. X plus h plus 4 down below, and x plus 4. So this is multiplication. Now, when this distributes here and there, the x plus h plus 4 is going to cancel that out, leaving only an x plus 4 times this 8. And when this thing distributes here, the x plus 4 is going to cancel that out, and resulting in this multiplying times that 8. So I'm actually going to kind of do all of that in one move. So limit, that's going to be 8 times x plus 4 up top, minus, I'm going to be careful about this, 8 times x plus h plus 4 all over h. And next line, distribute 8x plus 32. Let's take a look at what this would become. That would be 8x plus 8h plus 32. But we are subtracting this whole thing, and the subtraction would change the sign, so we are dealing with negative 8x minus 8h minus 32 all over h. And then from there, next line would say we would take into account that would cancel with that, right? Boom, boom, cancel, cancel, and then we have negative 8h over h, and these cancel. So we are left with, the limit of h approaching 0. Well, these just cancel, so there's no more h's anymore. So this just becomes 8. So we know for a fact that the slope of this tangent line at the point 0, 2 is definitely 8. So we therefore have our slope, which is 8. We have a point, which is 0, 2. And we can once again bust out the little trick of the trade to get our answer. B equals 2, and therefore it's going to be y equals 8x plus 2 for that one. Okay, suppose that the height of a projectile is shot vertically upward from a height of 60 feet with an initial velocity of 64 feet per second given by that thing. Compute the height of the object for t equals 0. Sometimes I find it helpful to actually get a sense of, the graph. I mean, it's a height of 60 feet, so it's like, okay. All right. At time equals 0, t equals 0, well, clearly, I wonder if there's a little bit of a typo, actually, because, if it's being shot upward from a height of 60 feet, that means that this y intercept should be 60, but according to this, the y-intercept is 80. I think that might be a typo. I'm going to choose to see this as 80. And therefore, compute the height of the object for t equals 0. In other words, when no seconds went by, right? Well, that would be the moment where it launched, right? And the height in that moment was a height of 80 feet. Now, you could figure that out by just plugging 0 into this. That would become 0, that would become 0, and then you would have 80 right there. All right, so the average velocity of the projectile for each of the following time intervals. So that's going to be the change in position all over the change in time. So like, you know, this, let's see, this right here, we could call time 1, and this one is time 2. And we want the change in position corresponding with these different seconds here. Now, I think it's probably helpful to realize that this is really just the slope formula. And this graph is like a runaway graph. If you think about it, you know, it's helpful to realize that this is time, and this is position or height or something, okay? So in other words, the x-axis corresponds to time, and the y-axis corresponds to position, and that's the worst looking position word I've ever seen, but let's just go with it. So the slope formula is y2 minus y1 all over x2 minus x1. Well, once again, these are x-coordinates corresponding with time, and these are the y-coordinates corresponding with position. So let's get clear on the time and position that is of interest to us. So let's recognize that at the end of the day, we will be dealing with x2 minus x1, which is really this 1 minus 0. So it's going to be 1 minus 0. But now we need the position that corresponds with 1 second. And in order to get the position that corresponds with 1 second, we can plug in 1 into this. And that would be negative 16 plus 64 plus 80, which is going to be 128. 128. And then we're going to have to subtract this y1, and the y1 that we are subtracting is the position that corresponds with this time, t equals 0. We already figured what that out. We already figured out what that is. That's 80. So it's going to be 80. And, where did we get that? We got it from this first part. Compute the height for the object for t equals 0. That's 80. So it's going to be 128 minus 80. So notice how this is the position that corresponds with this time. This is the position that corresponds with this time. And 128 minus 80 is 48. So that will be 48 over 1. And this one is also known as 48, and that's the velocity. So you're going to want to do the same thing with this, and be careful with the decimals. That's all. Okay, then it asks, what is the instantaneous velocity at t equals 0? We can keep in mind that the function we're dealing with is this. And I will just cut to the chase and say for this, you're going to want to use this one again. I'm going to call it h of t plus h instead of f of t plus h. Don't get confused by all the h's. This would otherwise be f of x plus h minus f of x all over h, right? But now we're sticking with their letter. Okay, and instead of an x, it's a t. Instead of an f, it's an h just because of that. All right. Now, if you were to go through the motions here, I'll tell you right now, I already know this is going to be the following. All right. And since we are taking interest in t equals 0, we're going to plug in 0 for t. And of course, that will be 64. All right, so that's that one. All right, given a function f of x, write a mathematical definition of its derivative. So, definition of the derivative, interestingly, we've been using that. That's this deal. So, for my student, your teacher wants you to be familiar with this clearly, and you are going to be using it here. My concern at this point is the fact that now they're asking for me to use the definition of the derivative, so I'm not exactly sure what they would have wanted me to use before. I mean, there's more advanced ways of finding derivatives. Maybe you've gotten into the power rule or something like that, and if that's the case, that's great. But I'm curious as to how your teacher would have wanted you to find the slope of the tangent lines on the previous page without using this, all right, at this stage of the game in your calculus class. It is going to be the case that you get into other ways of finding the derivative other than this, but usually in the beginning you use this, all right? So we could try it again right now with that, where it's like, f of x equals radical 1 minus 9x, and to be very careful, this is going to be 1 minus 9 times x plus h. And let's actually simplify that. 1 minus 9x minus h. So, using the definition of a derivative, that would be this. And the question is, of course, what are we going to do with this? I think to multiply by the conjugate is going to be a good idea. So this becomes the following. 9x, obviously it's got to be the same on the bottom. And what that does is cancel out the radical symbols. It becomes 1 minus 9x minus h. Now be careful with this part. You got to subtract the whole thing. So that cancels out. We still have this h down below, but that's being multiplied right now by this debacle right here. So we have 1 minus 9x minus h. And next line. This would cancel with that. this would cancel with that, giving me limit as h approaches 0, negative h over this h, one minus h. So now these cancel, giving me this. And substituting in 0 gives me this. Also known as this. So let's go back to the problem. We found it. Okay, find an equation of the tangent line to the curve at point 0, 1. Well, 0, 1 is the point. We have a point, which is fantastic. All we need is a slope. And if we want the slope, all we need to do is work with this and plug in 0 here. All right? And at the end of the day, what you will discover is that gives you negative 1 over 2. And going through all of the previous mentioned motions, you know, y equals mx plus b, that's going to be 1 equals negative 1/2 times 0 plus b equals 1, and therefore the equation of the tangent line would be that. Okay, sketch the graph of one possible function f of x for which all of the conditions are true. Write down what each condition tells you about the graph. Okay, I'll do the best I can with the sort of space here. The limit as x approaches negative 4 is infinity, so I'm only at this point going to take note of that. And if it's infinity, there's probably an asymptote there, so I'm just going to take note of that. The limit as x approaches positive infinity forever in this direction and negative infinity forever in this direction is 0, so it's kind of helpful to imagine even an asymptote here too. F of 0 is 2. That's something we could just plot right away. Boom. As x approaches 2 from the right, it goes to negative infinity. And as x approaches 2 from the left, it goes to positive infinity. Alright, so this one and this one are interesting. As x approaches negative 4, it goes to positive infinity. Negative 4 from the left. Well, I'm tempted to just draw that based off of that information. And as x approaches positive infinity, well, actually what I should have been doing is these 2's represent yet another asymptote. And let's focus here. When you approach it from the right, it goes down forever. So that's going to be like that. And keeping in mind, this is going forever towards the y value of 0 because of this green asymptote. That was denoted here, right? And then as x approaches 2 from the left, it's positive infinity. Okay, I think I see what my problem was before. This right here, this is a general limit. This is not approaching -4 from the left or the right. It's a general limit of approaching -4, and it goes to infinity. So what that means is that is a general limit of infinity as x approaches -4. And that's actually good to know because this can swing around and go up here, because as x approaches 2 from the left, it's supposed to shoot upward, which is what that does. All right. I am confident that that's the answer right there. Maybe you could clean it up by having this go straight through the 2, because f of 0 equals 2. Why not have it just cut through like that? Now, at the end of the day, it's a rough draft graph. It's ugly as hell, but it's valid. Okay, so that is that. Moving on. Investigate the limit, blah, 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 graphically, numerically, and algebra. Provide all the evidence necessary. Okay, so my student is more familiar with this converge graphical evidence thing. You could use your graphic calculator to do things like this. You know, all you'd have to do is probably, I mean, if you're checking out the left-hand limit, you want to get closer and closer to 0 from the left. So it could be that the teacher has specific numbers that you want to put in, but it could be things like this, right? Getting closer and closer to 0 from the left. And you could do something similar, even sort of mirror it over here, but make it positive, and therefore get closer and closer to 0, this time from the right, right? Because it's approaching 0 is what we're looking for. Now, if it's the case that these numbers, you know, go up as you get closer to 0, and if these go up as it gets closer to 0, then you might have a positive infinity on your hands. But you never know. You know, plug it into your calculator and find out. Now, I'm going to use the algebraic evidence. That's something that I can do easily right now by using the substitution. Now, if we were to just simply substitute 0 here, we'd have an undefined. So the first thing you need to do is get rid of the issue that's on the bottom. So that's going to be x, same scenario that you started with, but my student hopefully should know by now you got to multiply by the conjugate in this case. So here I go doing that, multiplication. That's going to be x plus 1 plus 1, x plus 1 now. We'll sort of transfer this over here because it's just going to look better. What we end up with on the top is this. I'm going to keep it all separate for now. And what we end up with on the bottom is x plus 1 minus 1. Let's not forget to write the limit. I decided I'm going to do that. And on the next line, I'll still preserve this x on the outside. It's a good idea to kind of leave it alone for a little bit. See what happens down here. Well, what do you know? Just an x, and therefore these cancel. And we end up with the limit as x approaches 0 is this at the end of the day. And that, if you plug in 0, would become 2. So what we've learned is that the limit is 2, which basically means that as you get closer and closer to 0, like this number right here is going to be really close to 2. And as you get closer and closer to 0, this number right here is going to be really close to 2. All right. I do believe that my student will understand everything I said. The only point of concern I have is in this moment they said use the definition of a derivative. Again, I would encourage my student to get clear about how you would have found the slope of the tangent line in previous problems without using this. As I said before, there are more advanced ways of finding derivatives to find like the slope of the tangent line. You know, there's more advanced ways, which you will be getting into, my dear student. You're going to get into a lot of advanced ways, but I just find it interesting that problem number 14 is the first mention of the definition of the derivative, so therefore I'm curious what they would have wanted you to use before. Anyway, that is that. It's actually very late. This video took me a little longer than I thought it would. But I like math, so it keeps my head in the game, the fact that I like it. But I hope this was helpful for my student. I hope it's helpful for anyone else watching. And good luck on your future exams.